This video covers Higher Human Biology Unit 3, specifically Key Area 7, Immunisation. It looks at the key learning outcomes of being able to describe how the existence of memory cells are used in vaccination, describing the function of the adjuvant, listing the different forms of delivering antigens through vaccination, explaining the importance of herd immunity, describing the herd immunity threshold, and giving the purpose of mass vaccination programs. Vaccination immunity can be developed by inoculation using antigens from infectious pathogens. So the immune system is exposed to antigens in a way that avoids the body becoming infected with the active pathogen. Normally, in order to generate the effect of the primary immune response, we have to be infected by a live pathogen. However, if we are exposed to the antigens from that pathogen without the live virus, we're able to generate immune memory cells, which means that future infections with the pathogen will result in a secondary immune response rather than a normal primary response. You should remember from Key 6 that the secondary response is faster, it produces more lymphocytes, and it lasts longer, so is more effective. Patients quite often do not develop symptoms and so are asymptomatic, but still manage to develop antibodies and fight off the infection. The role of adjuvants in vaccination. An adjuvant is any substance which makes the vaccine more effective by enhancing the immune response. It ensures that inflammation is produced at the site of vaccination and therefore that lymphocytes will be encouraged to come to that site and form the memory cells. Without adjuvants, it's perfectly possible that we might expose someone to viral antigens and their body just deals with it with a non-specific immune response, or uses a specific immune response to get rid of those antigens, but doesn't actually need to produce such a response that it produces memory cells. So it's possible we'd only mount a small response to the vaccine and not make sufficient memory cells. That's why it's quite important that we do cause a little bit of inflammation at the site in order to stimulate the immune response. There's many places we can get these viral antigens to use in vaccination. We can actively kill a pathogen, for example, using heat or radiation. This dead pathogen still contains the viral antigens on its membranes, so your body is able to produce memory cells using lymphocytes. We can inactivate the virus or weaken it, as we see at the top right. So often you expose the virus to for example, animal cells and cause it to be selectively pressured to evolve to become good at living in those animal cells. For example, eggs can be used. After a while, these pathogens have evolved to live well in these non-human cells, and when our body's then exposed to that pathogen, it's not able to develop and divide to give us a severe infection. So the pathogen is still alive with a weakened viral pathogen, but it's not able to give us a very nasty infection. The bottom two options, inactivated pathogen toxins or parts of toxins, we can either inactivate the proteins and molecules that the virus would normally produce to give us an infection, or we can just take the parts of the pathogen and expose our body to that. So you don't need the whole virus itself in order to generate immunity. You can just take some of its proteins that normally expose our body to during an infection. Section B looks at herd immunity. So herd immunity is the idea that if enough of a population is immune to a virus, then it shields those who are not, because the virus finds it very difficult to pass from one infected individual to another because it's very rarely exposed to a non-immune individual. If we look at these blue dots and imagine that this is a virgin population that has not experienced the virus before, if there is no immunity, if these red circles are individuals who have been exposed to the virus, every individual that they then come in contact with is able to be infected with the virus, and every individual there is exposed to is able to infect it. So you can see this entire population from 2 infected individuals can be completely saturated with the virus. If we have some level of immunity, so in this case, the blue people are still not immune to the virus, they are capable of catching it. If the red individuals only ever come in contact with yellow individuals who have either been vaccinated or previously exposed to the virus who are immune, it's almost impossible for that virus to spread because it never comes in contact with, so therefore can't spread through non-immune individuals. There's various factors that affect herd immunity. Herd immunity is very useful because it means non-immune individuals are protected, as there's a lower probability they'll come in contact with infected individuals. The herd immunity threshold, just to define it, is the percentage of the population who must be immune in order to prevent the spread of the infection. And this varies from virus to virus. It's affected by the density of the population. So in this case, on the left, on the right, there should be a roughly equal number of circles. On the left, this individual here is exposed to many different other individuals, very, very close contact. On the right, it's quite spread out. So this individual would have to go quite a long distance to contact as many individuals as they could on the left. So a very dense population makes it easier for the virus to spread. So you need a higher percentage of the population, so a higher proportion of them who are immune in order to really reach that herd immunity threshold. On the right, you can actually have quite a low population who are immune, and you still have reached the threshold. So you can see everybody on the left needs to be immune, and some people on the right who aren't. The type of pathogen, so those of us who have lived through the coronavirus outbreak will know that a lot is made of its R number, so the number of individuals that an infected individual comes in contact with and spreads it to. Social distancing was a technique to try and reduce the density, so the spread between infected individuals and uninfected individuals. And the different types of pathogens will have different methods of spread, so we'll have different R numbers. So, for example, a viral infection that is only spreadable through blood or other human fluids and secretions will be actually much more difficult to spread than one that is spread through breathing and through coughing, because most people will not, as a matter of course, put their body fluids into multiple people they have not met in a given day. Whereas we're quite often in the same room as someone who we don't know, and we breathe the same air. So the type of pathogen is affected by its method of spread, the number of people you're in contact with that method of spread. So different pathogens will have different herd immunity threshold. The efficacy of the vaccine. So even within a specific viral infection, for example, the influenza virus, flu, every year we get a slightly different strain of the virus, and therefore we need to use a slightly different vaccine. So we'll talk about that later on. So, for example, in 2009-10, the vaccine that was made for the flu that year was 56% effective. So if you were given that vaccine 56% of the time, it would make you immune to the flu. That can be to do with the fact that some people don't produce very good antibodies, or it could be to do with the fact that the vaccine itself wasn't very good at generating antibodies. It could be to do with the adjuvant or the flu itself. The next year, 60% of people who were given the seasonal flu vaccine would be immune. The next year, 47, 49, 52, 19 in 2014-15. So really, the number of people you would need to give that vaccine to would be very different in 2010 or 2014. Almost everybody in the population would really need to be given the 2014 flu vaccine for it to be at all effective. Because if you give it to 100% of the population, you're still getting less than a fifth of them are actually immune. Whereas in 2010, if you gave it to 100% of the population, 60% of them would be immune. So, herd immunity, we've looked at. Mass vaccination programs are a big issue within herd immunity. So in some populations, it's not possible to give the vaccine to a large proportion of the population. This can be to do with poverty or a lack of trust. Um, Historically, people from developed and rich Western countries um, would go to poorer nations or areas of their own nation and advise them on drugs and vaccines and procedures that will make them healthier. We are not always correct when we do this, and we have not always been completely honest and ethical when we have done this. So there are a lot of areas of the world who either don't trust or can't afford to have Western vaccines. So that's a problem with trying to mass vaccinate certain areas of the world. In some of the developed world, there's a percentage of the population who may reject the vaccine on a variety of grounds, whether they be valid or not. And so, again, it's very difficult to force 100% of the population to take the vaccine as we have freedom of will and choice. So, either because the nation is poor or because it's rejected, it's very difficult to mass vaccinate a lot of populations. We move on to antigenic variation, which is the last section of this. So antigenic variation occurs in the influenza virus, for example, and it's why we need to have a different vaccine every year. In some pathogens, the antigen on the surface can change in subsequent generations. So every time this virus replicates itself, some of the surface antigens can change. This means that the memory cells of your body, if they had made memory cells to a particular antigen, a particular protein on the outside of the virus, and then that virus stops using that protein in its membrane, you are no longer immune to that virus. So changes in these membrane proteins can mean that the lymphocytes membrane receptors are no longer complementary for that pathogen. And that would mean you would need to either be exposed to the infection again or have a different vaccine. So I said in influenza, this is a big thing. An influenza is quite a potentially serious infection. It remains a major public health problem globally. This explains why vaccination immunity must be acquired every year, and it's especially important for those who are vulnerable due to age or health conditions. We've looked at the existence of memory cells and how they are used in vaccination. We've described the function of the adjuvant. So the function of the adjuvant is to cause localized inflammation where the vaccine has been given and spur the immune system to come and make memory cells. We've listed the forms of different antigens and how they can be sourced for vaccinations. We've talked about weakened pathogens. We've talked about using inactivated virus pathogens. We've talked about using inactivated proteins, inactivated toxins. We talked about the importance of herd immunity and the herd immunity threshold, so the percentage or proportion of the population that needs to be immune for the virus to be prevented from spreading. We've talked about the purpose of max vaccination protein, so to encourage this herd immunity threshold, and the reasons why it might be difficult, so either through poverty or through rejection of the vaccine. We've talked about antigenic variation, so generation on generation, the change in the antigenic proteins on the outside of the virus, meaning that previous immunity is no longer necessarily good. And we've talked about why the vaccines for things like flu have to be given yearly, and it's to do with the fact that because of antigenic variation, your immunity does not last lifelong. It is removed when the antigens